Hi everyone, Dr. Pingle here with a final lecture on spatial interpolation. This is part 4 of the series Convex Hulls, Tins, Raster Resampling, and Image Pyramids.
These generally fall within the major topic of point-to-polygon conversions. So far we've talked mostly about point-to-raster conversions, but there are many cases where you might be interested in doing a point-to-polygon conversion. One of those we actually talked about in the last lecture, so that's the construction of Voronoi or Thiessen polygons. But we're going to be looking at a couple of different examples of this in this lecture. So polygon to point and line to polygon conversions do happen. In this case, what you are typically interested in doing is extracting the vertices. So that's a relatively simple task since all the polygons and all of the linear features are all made up of vertices anyway, or points. It's actually pretty easy to just drop those connections. What we usually do is work a little bit more often on point to polygon conversions. So this may seem kind of trivial, but if you kind of remember back to your childhood days, maybe you had to connect the dots. It turns out there's a lot of ways that you can connect the dots. So we'll talk about some of those here as we go on. So the tool that you'd be interested in using most of the time is going to be something like this one. So there's a feature vertices to points if you want to go from lines to polygons back. So again, this one's pretty straightforward. We're just going to be dropping the connections between the points, and what you're going to get back is a point data set. When we want to go the other way, we're going to be working with what's called a Delaunay Triangulation. So the idea here is we're going to connect all of the points to nearby points, and we're going to do it in a way that forms a bunch of triangles. Now the triangles that you see here at right, this is a Delaunay Triangulation. The triangles that you see there are a special kind, and what we need to do, or what the algorithm tries to do, is to create triangles by maximizing the minimum angle. So what we're trying to do is produce sort of equilateral-ish triangles, and what we're going to try to avoid doing is making a lot of long, skinny triangles. Typically that's still going to happen, especially around the edges. So if you look at this one, you can see a couple of these long, skinny triangles as you get close to the edge. But generally speaking, the algorithm tries to avoid that. This is an active area of research, so it's plenty of algorithms can solve this problem, but especially when you're dealing with millions of points, being able to do that efficiently is important. And so it's still an active area of development, coming up with faster and better ways to create a correct Delaunay triangulation. Delaunay triangles are actually used for a lot of different things. They're used in one kind of finite element modeling, or numerical modeling more generally. And the idea is that if we can partition the space and create these tiny little triangles, what we can do is we can simulate how movement or contaminants or water or whatever it is that you're modeling moves through the system by basically moving from one triangle to an adjacent triangle and just doing that kind of over the long term. In this case, this was a mesh that was made to model groundwater flow. We used a jet color map that goes from blue to green to yellow to red to show elevation. And one of the things that you'll notice about this is that the triangles themselves can vary quite a bit in size. And so you can create more triangles where you want to have a finer resolution, and you can have larger triangles where coarser resolution is fine. This particular finite element model came out of a groundwater application, so this is called fee flow. Flow is the flow of groundwater through the system, and you can see a polygon representation of that in the image at the left, and a mesh representation at right. And actually this particular one extends in 3 dimensions, and so we have the mesh on top, but the mesh actually extends down several layers as well. So we can model flow not only horizontally through the system, but vertically as well. A Delaunay triangulation has kind of an interesting property. and that is that no fourth point is within the circle circumscribed by the points on a triangle. So if you take a triangle and you use those 3 points to make a circle, no other point will be within the bounds of that circle. If you take a Delaunay triangulation and you did a union operation to dissolve all of the differences between these, what you would be left with is what's called a convex hull. So this is the line that goes around all of these points. And you can imagine that the convex hull is essentially what you would get if you put a rubber band around all of the points. So the convexity means that it doesn't dip inward at any point. To illustrate this concept, what a convex hull would look like, I've created some random points, kind of a little used feature in ArcGIS, I think, but a useful one at times. You can actually create random points anywhere within your shape or within your view. So what I've done here is I've created 100 random points within the city of DeKalb boundary. And what I want to do is I want to connect all of those up and see what kind of a shape I get when I try to recover the shape of DeKalb with these tools. So the first thing I'm going to do is going to create a tin. So there's a tool that just says create tin. The tin is an object that we're going to talk about a lot more when we get into discussions about elevation in future lectures, but this stands for Triangulated Irregular Network. So this is kind of what we just saw. It's the result of a Delaunay triangulation, I guess is probably the easiest way to say that. So what you get here when we've done the union operation here is a convex hull around all of those random points. So you can see a couple of them peeking out at the edge. Now, one of the things you'll notice about that convex hull is that it doesn't do a very good job of retaining the original shape. The original shape of the boundary of DeKalb is fairly complicated, and even if we had added 1,000 points, we would only be doing sort of a marginal job at going from points to polygons. So this is one of the reasons why this is a more difficult operation than you might think. Tins are actually their own particular data type, so they're not really. They look like a vector data set, but they're not. So they need to be stored and they need to be symbolized a little bit differently. So if you go to symbolize a tin, you have to control the appearance of the face and the edges. So the face is going to be the triangle, the edges are going to be the lines between them, and the nodes are going to be your original points. This is the underlying Delaunay triangulation for all of those random points drawn on top of DeKalb. And it forms what you would just generally think of as a network. So as I said, in ArcGIS, the tin is a data type of its own. So you can see there that I've pulled open a dialog box looking at the data type for this feature, and you'll see that it's listed as a tin. So ordinarily we think of vector and raster as being sort of the only data types in GIS, but at least within the ArcGIS world, that's increasingly not true. But that doesn't necessarily have to be true for all tins. So in QGIS, if you run a Delaunay triangulation operation, what you get back at the end of it is just a standard polygon layer. The upshot to that is when you want to do an export, things get a little more complicated. So here I just have a dialog box open, and it's a little more difficult to get the data in and out that way. Typically, what you would use a tin for is to represent elevation data, and so we'll talk in some greater length about this when we talk about elevation. But the idea here is that what we want to do is we want to create a vector data structure to describe things like elevation, and we know that in many places elevation doesn't really change that much, or it doesn't change. There's certain parts where it doesn't change that much. What you can do, is basically use larger triangles in places where the landscape doesn't change very much, and in places where the landscape does change, you can use smaller triangles to kind of keep the high fidelity between the tin and the elevation. The idea behind tins was that it was supposed to save storage space. Instead of having one cell everywhere across your study area, you could eliminate some of those cells because they're just redundant information. If you're modeling a flat plane, you don't need hundreds of pixels to do that. You could theoretically do it with just 3 or 4 points. As it works out, it's actually a little more difficult for the computer to keep track of these kinds of things. They tend not to produce as much storage savings as you would think. And so as a result, tins are not used all that often for analysis, although there are some definite exceptions to that. But they are frequently used for visualization. It does fit in very well with how other computer graphics are rendered. And so tins kind of find their way into GIS and other communities that way. This is an example of how you would go about creating an elevation tin. So here we've got sort of an elevation layer. White is higher, black is lower, and around that we've got the red boundary of the city of DeKalb. The idea here is what we're going to do is use each grid cell within the elevation raster as a point. So we often think of, again, rasters and vectors as very different, but you can imagine that for each square in your raster, the center of that square is a pixel, or it is a pixel, and the center of that pixel is you could represent as a point, and so any raster is basically you can imagine just as a collection of points. The tools within ArcGIS are pretty straightforward. So using the raster to tin tool is going to do all of the work for you. You don't need to convert rasters to points and then points to tins. This will do all of that for you. This is the example of what that dialog box looks like. So you specify an input raster, you specify an output tin, and then you would specify a couple of things. And the two that I really want to mention here are the Z tolerance and the maximum number of points. And both of these are going to be aimed at thinning the tin. So what we don't want to do is just connect every pixel to every one of its neighbors. Because elevation doesn't change that much, what we want to do is only connect things up where there's a lot of difference. So this is an example of what that might look like in the city of DeKalb again. We have the Kishwaukee River Valley flowing through the system here. And one of the things is that the triangles get much denser or much smaller as you get into places where the elevation changes rapidly. So within the river valley itself, the triangles are quite a bit smaller. Once you get outside of that, the triangles tend to be a little bit larger. So we're essentially spending our resolution data where it matters the most. This is kind of I know this looks a little bit clunky. This is sort of the default symbolization for this. We'll show you something that looks a little bit better here in a second. This is just an example, not a fantastic diagram here, but this is showing you what connecting almost all of the pixels to all of their neighbors would be like, except for this big sort of blob-like structure on the left. So this is an extremely dense tin, an unnecessarily dense tin. So most of the time what you're going to see is tins more like the former slide than this one. So tins work in one of two ways. We either are going to specify a Z tolerance value, or we're going to specify the maximum number of nodes. And both of these are going to work kind of similarly. What we want to do is we're essentially going to take our original data. So in this case, this is sort of like a profile view. The raster is in blue. And we want to create a tin. We want to connect all of these points. But we're only going to connect points up as long as they're within this tolerance value. Anything outside of that we're going to exclude. So a smaller z-tolerance value is going to make for a smoother, denser net with more nodes. You know, this may be important for you if it's important to kind of keep this as a high resolution model, a high fidelity model. Then you can set that z-tolerance value very low, and you're going to have a denser net that better represents what you're trying to show. Within GIS, this algorithm is called the very important points algorithm. It's been around for 30 years. It's effective, it's relatively fast, and it's a very useful way to sort of eliminating all of these extra redundant points. One of the cool things, and we'll get into this again more when we look at elevation, but TINs are really most useful for visualization. And so if you use ArcScene, which is ArcGIS's three-dimensional package, you can actually load TINs up and look at them and rotate them in perspective view. And you can get a lot of really good information this way. So this is the TIN of elevation for DeKalb that we've had to vertically exaggerate a good deal. As I said, the point to polygon conversion is somewhat difficult. Most of the time, what we do is we use a convex hull around the set of points. So again, this is, imagine sort of a rubber band around the points, what it would look like, where it would stretch. So we have a shape here that looks kind of like a bunch of points that make sort of like an A shape. And the convex hull is basically going to be drawn around that whole thing. It's going to look kind of like a blob. What we would like to be able to do is do a conversion of point to polygon where we're really able to identify places where there are no points. So we would identify this A-looking structure. As it turns out, so this process is the creation of what's known as an alpha shape. So we need algorithms that are going to be able to sort of move in on the sides of those points, rather than just sort of leave these big empty structures a part of the polygon. There are lots of ways to kind of move from points to sort of an encapsulating shape. So this is one example of that. So this is the minimum bounding geometry tool in Arc, and there are lots of different ways that you can define that. So you can define a convex hull. You can define rectangles by area, where it's going to try to make this the smallest rectangle with the smallest area around all of your points. There's a similar sort of one, rectangle by width, which is going to try to draw it doesn't minimize area, but instead it minimizes the width, one of the sides. You can create a bounding geometry of a circle, and you can create a bounding geometry of an envelope, which is essentially just a bounding box. Alpha shapes can exist. They do exist in other forms. We have a sort of this, again, threshold parameter that's used to try to find the boundaries around your lines. So in this case, I've drawn something that looks a little bit like an H shape. And depending as you start to relax, as you start to increase that alpha parameter, from here it is at 0.1, moving all the way to 0.3. It starts off as something that's maybe not quite as bad as the convex hull, although it's not off by much, into something that looks more like an H shape. But you'll notice that as that parameter gets too high, we start cutting out some things on the interior of the H that we probably wouldn't want to. So picking that parameter can be difficult. It's one of these things where algorithms are really they're okay at this, but there's still a lot of work to be done to do this well, or to do it in a way that is anything like the way a human would do it. This kind of brings up another topic that's important. So that's the idea of shape simplification and densification. So whenever we're doing these conversions, in this case we're looking at point to polygon conversions. There's this idea kind of underlying it all that we don't need all of the points to sort of represent what we're trying to represent. effectively. So there's a push within GIS to try to represent things as simply as you can without losing what it is that you're trying to represent. So there's a really nice example of this online. I think I posted the URL for this previously, but you can kind of play around with it online. This comes from Mike Bostock, and we've got line simplification applied to the bounding geometry of the United States. In the image at left, we're using 22% of the original points. Things look very good. The coastline, especially in the east and southeast, looks relatively intricate. But you can reduce the number of points in that boundary all the way down to a little bit less than 1%, and the United States is still quite recognizable. So it really just sort of depends on what you're after. But most of the time, you can pair out a lot of the shapes, or a lot of the points rather, and still keep a good high fidelity matchup to your original polygon. So why do we simplify? Partly because spatial data is often unnecessarily complex. More often, we've got limitations with respect to the cartography. So we talked early on about using very complex geometry can sometimes make the map appear messier than it would if you simplified the geometry. Simplification is also important for reducing the computing resources required to solve a problem. So it's much better, much easier for the computer to run an algorithm on 1,000 points than it would be to run it on 1,000,000 points. So if you can simplify things down a good bit, you can cut out a lot of the work on the computer. And simplification may actually produce better outcomes, especially when trying to replicate human behavior. So if you're trying to, for instance, model the route that human beings might take through mountainous terrain, it turns out that using the highest fidelity model, elevation model, doesn't actually replicate the way that humans think about their environment, because humans smooth out, their sort of perceptual filters smooth out the environment as it is. So if you want to model the way humans do it, maybe simplification actually gets you closer. This is the URL if you're interested in taking a look at the at Mike Bostock's map and simplification algorithm. It's an interesting project because one of the things that he does is use the Visvallingham and Wyatt algorithm to dynamically simplify based on the movement of a mouse. And the reason that's kind of cool is it shows you how dynamic and interactive the process can be. But it also sort of can be very helpful in illustrating how some of these algorithms work. So the Visvallingham and Wyatt algorithm that drives that works something like this. If you've got 6 points and we needed to decide how we were going to simplify that line, one of the things that we do is this is the way the algorithm works, we would draw lines sort of forming these triangles between each adjacent point. So 1, 2, 3 form a triangle, 2, 3, 4 form a triangle, 3, 4, 5, and so on. And the way the algorithm works is we look for the area we look at the areas of the triangles, and we choose the smallest one, and that is the one that we eliminate first. And so it's kind of an interesting way of solving the problem. So we would eliminate 5 first, and then we would recalculate. At this point, 3 has the smallest area, so we'd remove that point next. At that point, 4 has the smallest area, so we'd remove that point. And we keep that process continuing on until only the endpoints remain. And so we have this sort of series of points in order of which points are most important and which points are least important, which enables this sort of dynamic filter to be applied. There are plenty of different cartographic tools for generalization. You've looked at a few of these in earlier work. But good to sort of see these again, and especially get a little bit more of the theoretical treatment as to why they work. Every time that you're working with projections, by the way, you're also doing an interpolation. So we talked at length about interpolation in the previous lecture. Interpolation is something that's going on all the time behind the scenes. And so I thought it'd be worthwhile to talk a little bit about that. So many kinds of data come to you in different coordinate systems. So you might download the boundary of the city of DeKalb, and that's in WGS, but you may download an elevation layer that's in, the city boundary of DeKalb is in UTM rather, or the state plane coordinate system. But you may download something else like elevation data that comes to you in WGS 84, or just latitude and longitude more generally. And when that happens, you've got this mismatch between coordinate systems. ArcGIS is going to, behind the scenes, reproject that data so that everything lines up. It's one of the things that makes ArcGIS so handy, and GISs in general, is that you don't need to sort of manually make everything line up. You can just trust that the GIS, as long as the projections have been defined at the beginning, you can trust that the GIS is going to do that for you. So that's really a useful thing that GISs do. But it's important to know that behind the scenes, it's going to be sort of interpolating that for you. And so it can be really helpful to know how to use the resampling techniques. So this is an example of using resampling to sort of reproject a raster. So we're using the project raster tool. We're giving it an input raster. We're specifying the output raster. We're specifying the output coordinate system. And importantly, and this is key, we are going to be specifying a resampling technique. Now, this is technically optional, and if I had my druthers, I would force people to sort of choose off of a list, because nearest is usually, in my experience, the wrong option. So if you're doing a resampling on something like an elevation raster, you're really going to want to use either bilinear or cubic to make that judgment. We looked at nearest neighbor interpolation in the last one, and basically what you're going to get is a very blocky image. And the help tells you about that. It'll say that it'll say the nearest option is the default since it's the quickest, and because it will not change the cell values. Do not use nearest or majority for continuous data such as elevation surfaces. So it's right there for you, reminding you, but I still have a sense that probably most people just hit OK without ever really thinking about it. So you really want to use bilinear or cubic options. So those are going to be, smoothing the data out, making reasonable guesses, instead of just sort of taking whichever point is closest. The other one that you would sometimes want to use is the majority resampling. So this is especially useful if you're using something like a land use class, or when you're working with categorical data in general. What this is going to do is it's going to say whatever there are the most of, that's what I'll use to represent it. So if you're using nominal or categorical data, you'll definitely want to use majority resampling to do that. One of the kind of overlooked areas that's really important is that you can specify registration parameters using environments to snap a raster or to declare a particular size or shape or extent of the raster that you want to create. So most of the time, probably just using the input geometry is going to be fine. But there may be cases where it's really important to you, if you need to do raster calculations, that they line up one underneath another. So defining a snap raster can be very helpful there. Image pyramids are kind of the last major topic that I wanted to talk about. So you probably have run into these things via a dialog box that I'll show you here in a second. Every time you load a raster, it might prompt you and say, "Did you know that we don't have any image pyramids for this, and would you like me to calculate them for you?" Most people just hit OK, but they don't really understand what it is. So this is what it is. What it's trying to do is it's trying to say, well, you're not looking at the image at the highest possible resolution all the time, right? You may be very zoomed out. And if that's the case, it's more efficient for the computer to sort of create these smaller versions of that. So we kind of ran into this a little bit when we talked about map tile servers. So the idea here is that if you know the zoom level that you want to look at, it's cheaper, it's better on the computer, it's going to be faster to pre-compute these image pyramids rather than sort of re-rendering the original data. This is the dialog box that you may see when you load an image. So this is some data that I brought in, and it says, you do not have pyramids for this. Do you want me to calculate those for you? It's almost always a good idea to do this. You'll notice though, and this is why I wanted to talk about this, is that there's a pyramid resampling technique, and you can decide whether you want to use nearest neighbor, bilinear, or cubic. Here again, nearest neighbor is the fastest, but it's not necessarily the best. So what I would recommend is taking a moment and letting it do the either bilinear or cubic. Both of those work out pretty similarly. But do something a little bit better than nearest neighbor, because you only really need to calculate this stuff once. If you've loaded your raster already and you've told it that you didn't want to compute the image pyramids, or maybe you need to do that from scratch, maybe you selected nearest and you changed your mind and you'd rather have this stuff be linear, you can recompute pyramids anytime. So there's a build pyramids tool, and that tool is going to basically rerun and re-aggregate those different zoom levels for you, so things will be a little bit snappier. So to sum up, I wanted to say that interpolation is always an error-prone process. So interpolation is the process by which you make guesses about intermediate points where you don't have any data using the data that you do have. Anytime you make a guess like that, things can not work out. You can make mistakes. You're just making guesses about what's happening in the meantime. And it's okay, maybe it's a stretch to say that anything can happen, but a lot of, the environment is very variable. You don't really know what goes on between those 2 points. So anytime you do an interpolation, and this is getting to the second point, what you want to try to do is minimize the number of successive interpolations on the same data. So if you downloaded your data and it's in latitude and longitude and you convert it to UTM, that's great. If you then decide, oh, I would actually have preferred this to be in the state plane coordinate system, you're better to go back to your original data and go from WGS 84 latitude longitude to state plane than you are to go from the one to the next to the next. This is sort of like making a copy of a copy of a copy, and the more times you do that, sort of the worse things get. So you do want to be careful to sort of only do it once or maybe twice. Once is a lot better than twice. And then finally, you want to balance speed and accuracy. So most of the time, things that are going to be better interpolators are going to be a little bit slower. That's not always the case, but that's often the case. So these speed accuracy trade-offs happen with interpolation just like they do in other domains.